So, have you ever wondered how an AI in a game knows exactly where to go, or how a robot learns to walk? Well, behind a lot of that intelligence is a really cool framework for making smart decisions over time. It's called a Markov decision process, or MDP for short, and today we're going to break down exactly how it works. But before we dive into all the components, let's start with a question that we humans face all the time. Do you take the small, easy win right now? Or do you hold out, play the long game, and go for a much bigger payoff down the road? This is the fundamental trade-off at the heart of all sequential decision-making. To really get a feel for this, let's look at a simple, everyday scenario. Because our choices are rarely just one-and-done deals, right? They're part of a chain, where what you do now directly affects what you can do next. Okay, picture this. You're at a train station. You could shove your way on the second the doors open. That's a quick win, you're on the train, but now you have to spend the next 10 minutes fighting through a crowd just to find a seat. Or you could wait just 30 seconds on the platform, let the initial rush pass, and then walk onto a much emptier car and grab a seat right away. See, the best immediate move, getting on the train fast, isn't actually part of the best overall strategy. And that train problem, that's exactly the kind of thing Markov decision processes are built to solve. They give us a formal language, a kind of mathematical grammar to map out these complex problems. It turns our gut feeling dilemma into a structured model that an AI can actually understand and work with. Now, this whole framework is built on one core, really powerful assumption, the Markov property. All this says is that the future only depends on where you are right now, not the long winding path you took to get here. Everything you need to know to make the best next move is contained in your current situation. So to actually build one of these decision-making maps, our MDP, we need 4 key ingredients. Think of it like a recipe for defining the world our AI is going to live in. Let's take a look at each one. First up, we have states, which we just call S. A state is basically a snapshot of the world at a single moment. If our AI is a little mouse in a maze, then every single square it could possibly be on is a unique state. Second, we have actions, or A. These are pretty straightforward. They're all the possible moves the agent can make from any state. So for our little mouse, the actions from most squares would be to move north, south, east, or west. Simple enough? Third, and this is where things get really interesting, is the transition probability, or P. These are the rules of the world, the physics of our environment. They tell us how likely we are to land in a new state if we take a certain action. For example, maybe the maze floor is slippery, so if our mouse tries to move north, there's only an 80% chance it actually works. The other 20% of the time it might slip and stay right where it is. This brings uncertainty into the mix. And finally, we have the reward function, R. This is the feedback loop. It's the signal that tells the agent what's good and what's bad. Finding the cheese at the end of the maze might give a big, juicy reward of plus 10, but every single step could cost a tiny negative reward, like -1. This is clever because it encourages the agent not just to find the cheese, but to find it as efficiently as possible. And boom, there you have it. The states, the actions, the transition probabilities, and the rewards. These 4 things together make up the complete blueprint of our problem. So now that we've described the entire world, how does our agent actually win? Well, winning in the world of MDPs means finding the absolute best strategy you can. And in the lingo, we call that an optimal policy. So what is a policy? It's really just a plan, a rule book. You can think of it like a Mac that tells the agent, for any state you find yourself in, here's the action you should take. It's the agent's complete guide to behavior. And the best policy, that's the optimal one, is the one that racks up the most reward over the long haul. Not just on the very next step, but over the entire journey. That's the key. We want to maximize the grand total, the cumulative reward. But how do we even define the long haul in a mathematical way? Well, the answer lies in this little variable called the discount factor, or gamma. It's just a number between 0 and 1, and it's basically a patience meter. If gamma is high, like 0.99, the agent is super patient and cares a lot about future rewards. But if gamma is low, close to 0, the agent becomes really short-sighted, only caring about the prize it can get right now. Okay, so up until now, we've kind of assumed our agent knows all the rules of the world. But what if it doesn't? What if we just drop it into a new environment with no instruction manual? Well, this is where a brilliant algorithm called Q-learning comes into play. It lets an agent figure out the best policy through nothing but trial and error. At the very heart of Q learning is a simple grid called a Q table. Honestly, the best way to think about this is as the agent's cheat sheet. For every state and for every possible action from that state, it keeps a running score. This score is its best guess of the total future reward it's going to get if it makes that move. And the whole game is to fill out this table with the correct value. So how does it fill out this cheat sheet? With every single step it takes, it uses this update rule. Now, I know that equation might look a little intense, but the idea behind it is actually incredibly simple and intuitive. Let's break it down. The new value it calculates is just a mix of two things. On one side, you have the old value, what it used to think was the right score for that move. And on the other side, you have this chunk of new information based on what literally just happened, the reward it just got plus its best guess for the value of whatever state it just landed in. So the learning process is this constant cycle. The agent tries a move, it sees what happens, it gets a reward, and it looks at its new position. Then it asks, okay, from this new spot, what's the best I can do? And it uses that new insight to just slightly nudge its old belief. Over thousands and thousands of attempts, these tiny little updates make the values in its cheat sheet get closer and closer to the true optimal scores. This might all seem a little abstract, with mice in mazes. But the real power of this framework is just how incredibly flexible it is. So let's see how these ideas jump from the theoretical world into our world. I mean, the impact of this stuff is massive. MDPs and reinforcement learning are the foundation for training robots to walk and balance, for developing automated financial trading strategies, for creating personalized treatment plans in medicine, and, of course, for building AIs that can master incredibly complex games like Atari or Go to a superhuman level. So when you boil it all down, the main thing to remember is that Markov decision processes give us this powerful, unified language. It's a language for talking about any problem that involves making a sequence of choices to reach a goal, especially when the world is unpredictable. From a simple choice like boarding a train to managing a global supply chain, the underlying principles are exactly the same, which leaves us with a pretty fascinating question. Now that we have these incredible tools to model and solve such complex decisions, what are the most important problems we should point them at next? Thanks for tuning in.